Thank you very much for the invitation. So it's a pity that Alessandro Chiodo is not here. And we'll talk about some classical which studied. And the talk is in fact not so much about geometric methods. At the end, we're going to get some numerical analysis of the intersection and verbal and the moduli case of curves. But it's done by completely non-geometric methods. And so an overall question we'll have to most of you who are algebraic geometers is, can one explain this vanishing geometry? Capacities. Behind there's a moduli space. I fix G and N, G minus N positive. And we want to look, so one takes our positive integer, any integer that I'm going to assume take something positive. And then I look at integers. And I need the divisibility condition, which is that the sum of the AIs is 2D minus 2% S. Then one wants to consider the moduli space M, G, R, S, A, so the n tuple of A's. So which characterizes G with curves with n points, with a line bundle over C, and you want that these line bundles from an isomorphism of L to the R with K log the power S twisted. We have some zeros and everything. We call this moduli space and we compactify it some way. And then you look at the universal curve like this. And over this universal curve, you have the universal line bundle, whose fiber is just given by this. So let's call this map. And then if you want, you can forget about the line bundle and go back to mg and bar. Call it epsilon. And the construction for the Chiodo class, I'm going to denote omega G RSA. You're going to take the derived put forwards of L. So you take the dual and the trend class, and then push forward the moduli space. So you get a class on the moduli space curves that depends on this Swiss parameter A. This class is tautological and you can compute it. An expression of kappa classes, psi classes, boundary divided. Let's take a simplest example. To take R equal S equal 1. You were looking here at the bundle of holomorphic forms, the Roth bundle. So what you have is a dual of the Roth class. are well, R-spin generalization of the whole class. So there's a what we call the fundamental line. Interested in whether they belong to the zero R-1. And one property of this class is that if you were inserting an into a R slightly off the fundamental domain, it's the same as anything out of the zero. Okay. And then in the notation, if I have an integer m minus n bar, with the unique integer between n for length, like that minus n bar is minus n modulo r. So we're going to be interested in intersection of this class with type classes, and in particular in the following intervals. So the Venus Rx and on n talking of positive numbers. If you want, you can order them to depend on the partition view, and it depends on some with E, and by definition, this is the integral of the Chiodo class with parameters minus mu bars, so you apply the bar operation to each of the mu's, and to the b's. And we're going to put psi class insertions at a very particular time. 1 minus ui over r psi I. So we want to study, we're going to say something about those. The reason why we study those integrals is because they appear naturally in curve counting theories. Okay. About very symbols. Hermann's number is the one I want to look at in P1 with 3 points. And Hermann's theory is about counting branch covers in P1, ramified in a certain way over 0 and infinity. Let's say we're clear about division over 3. Multiplication of order 2. So that means again that I have a partition with a row of size 3 and a row of size 2. Like new. And on the other side, we have another indication. Let's say this, so same degree 5 here. So that would be represented by the partition in the row of size 2 and in the row of size 1. And on infinity, I can become. In the middle, you may have some other points. Then you don't want to necessarily specify what happens. You may have some triple ramification, some double ramification, and so on. And then, of course, you need to complete the picture in a curve, which maps with the branch cover to P1. So Hermann's numbers are essentially counting such maps with some verification information. Okay. And then because these kind of automobiles we want to cut them by their symmetry. If your cover is connected, you have this theory that tells you how to find the genus. That the length of the particle in lambda and nu, which corresponds to the number I created is 0. And this is going to be the number of other branch points counting with non-existent. Okay. So the degree is the size of the one. So computing Hurwitz numbers is a classical problem. We got a new term about 25 years ago, where in fact this problem can be addressed by intersections. This is the famous formula of Ekedal, Galgo, Shapiro, and Van Pine. They tell you that if you want, I'm going to call A, B, nu, and here we just pass no ramification about infinity. And this is the case where elsewhere, that all those points, you assume that they are simple ramification points. Simple branch points with only one this picture everywhere. You already know how many there are. And the ENSD formula is non-collateral factor is explicit. And then we take on the hot class, which is what I call I11, the dual hot class for nu. And then no extra measurements. With this integral, I don't have this, I just have as many factors insertions here, and you can almost forget about the bar. You can even forget about that because r is equal to 1, so there's no there's only one twisting fundamental rank. So this is numerated as the hot class, the dual hot class, and you have 1 minus nu I psi r. Then you can consider other types of branching here or here, and you have various generalizations of this. There's one which is R orbifold. Where you can take a simple branch point in the middle, but now you're going to take here part which is a rectangle. So all the previous involved infinity are the same order. And this, there is some combinatorial factor, and this is IG RR nu. The Chiodo class is parameter R.
I'm sorry, can you repeat the definition of simple?
Simple. So the simple branch points is only one previous equals 2 and the other.
Okay, thanks.
So you may be interested in arbitrary partition here, and here it starts to get more interesting.
Okay, should it be like R to the power mu to the
Should it be R to the power 1?
no in H?
So I just, yeah, sorry, R. So for this, there's a formula to plot on the and saying, and it goes as follows. So mu and lambda are arbitrary particles of the same size, degree, and you have to fix some r. So there's no r in this problem. Contrary to here, you fix some r big enough. And what does big enough means? It means that maybe right here. So lambda 1 is smaller than R, the largest part is smaller than R. And you also want that the max, we start to merge two rows. Be smaller than R. Maybe I can move on to this. And then, so again, we keep the formula, which is not the integral over mg and bar, but over mg and b z to zr. It was then later shown to be equivalent by Levansky, I think Popolitov, Sharigan, and Zvolkin. I'm not really sure about it. To be equivalent to an integral over the moduli space of curves. And what you get is, so here R, one collateral factor, there's u, and then you have extra parameters, which are, so lambda prime. And what is lambda prime? You start to your partition lambda 1 is the box of size R. You may have some parts of size R. And I'm just removing those things. Removing the parts of size R, and I have on that. So we can in principle compute all of these numbers with Chiodo class.
How does the third one imply the second?
How does this one imply this?
Yeah.
So in that case, you only have parts of size R. So this thing is it's not that prime and
in the definition of the Chiodo class, the denominator looks like almost like the normal bundle to smoothing some nodes. Is there a geometric interpretation of that?
of this.
Yeah, there's the denominator.
So if you shift by multiples of R, the twists, you get expression of this kind. However, I cannot say that this is exactly your Chiodo class itself on some instance.
But it is the residue normalization. It's a vertex term, the residue. That's the geometry.
Okay.
How this thing is proved that the merging of MD and B cyclic space is proved by localization in the moduli space of stable mass from static to 1. The static point of order R has so you can wonder what, so this R is a bit arbitrary, so you just take it large arbitrarily. But what happens if you don't have this condition to see boundaries? So let's say this the opposite of that condition. There's another thing which JDT is doing is in fact you can also get some vanishing. So here mu 1943 lambda, but actually you treat differently the parts of size R and the other parts which are small. What you can think of is I'm going to define extending the R extended part. We have parts of size 1, of size 2, and 2 size R. And you're going to allow this one to be negative. In that case, of course, there shouldn't be any Hertz number. So this left-hand side is 0. But the formula somewhat still holds, and you do have vanity. So if you take lambda, which is an extended partition. If lambda is an extended partition, or extended partition. That lambda prime is bigger than mu plus is boundedness. We put the word reach. Then you get this. That is easy. So that's a good proof. So what we ask ourselves, I mean, by the Victor theory, is what happens without boundedness. And so that's here in the for third one, we're going to take slightly more setting where I is not equal to f, but it's multiple of f. I want s, which is bigger than 2, e bigger than 1. And then I'm going to write something like that, some number. So this is doubled, so this h simple like that. When d is equal to 1, and then r is equal to s, I will get back this number. Otherwise, another type of Hurwitz number that differ by what do we allow in the middle. It's not necessarily simple ramification. And this has an expression, but then you have a sum of further integrals. You look at lambda. Lambda 1 is smaller than r. So you remove the r parts. And you look somewhere the length of the rest. Then you have to sum of all ways of decomposing into k partitions. The partition S minus lambda. In such a way that the sides here are smaller than n minus 1. I will get my partition in the box. Here is R. So I forget about that. This is my lambda prime. And then this partition which I see here is what I call S minus lambda or S minus lambda prime. S minus lambda will have some zero length over time. So this is S minus lambda. Then you have some explicit fundamental factor. And a further integral. And here what we got. So for each I, you have a row I, a partition, you do S minus the side of this row I. And that's given the fundamental range because you impose that the side here is smaller than S minus 1. And F of row is a Pocamer symbol the right wheel factorial. And then remember more. Doesn't matter so much more. Okay. And there's going to come another time.
Sorry, did you define capital DH, or were you going to, or?
Did I define? No, I didn't. I'm just saying it's some kind of wave resistance. The wave being not only for synchronization in the middle. If I was cutting lambda, which is, let's say, f over x, so it has to do with d plus 1 completed cycles in the middle. But it's not exactly that. So the remark is that if lambda prime has size bigger than nu, so this is also true for extended particles, then of course there's no Hermitz numbers. So this left-hand side would be 0, and therefore you get that this combination back. If I want to write it in terms of, I call that nu. Can you express what is this condition in terms of nu, taking into account divisibility, which said that anyways you're going to get 0 for trivial reasons if you don't have some congruent condition. So the condition is that mu plus nu is smaller than s length of mu minus. Then you get vanishing of that integral. So lambda prime is f minus 1 in the sense we did before. So I can write in terms of nu. That means that the minimum when you merge two rows is bigger than s. In that case, the only type of decomposition you can make, because you're forcing this on all the sides of these parts to be smaller than s minus 1, is just a trivial thing where you just take each row of nu is a row. So each row I is a partition with length 1. Row I up to permutation is just a partition with nu I, so you just get one term. And you get the T value. In the case R equals x.
Excuse me.
Yes.
Have you thought about how these relate to sheaves with co-invariants from vertex algorithms, like affine vertex algorithms? These numerics are almost identical.
So
Yeah.
you do when you consider this bundle of control blocks into the trend class, you also can compute those classes. It's not exactly that one. It's not a Chiodo class, something different.
Oh, really? I mean, oh, okay.
Yeah, it's totarical classes. You have some R matrix, you can express everything in the boundary dividers, kappa class, psi classes, but it's not a Chiodo class.
Okay. The vanishing, the numerics on the vanishing, pretty much identical.
Okay, you should discuss.
Interesting.
So what I will try to come in to just explain that, okay, I'm going to give two more of these theorems. And I'm going to try to give you an idea why there are two, and you come with a systematic approach, which is not at all geometric, which in principle you can try to apply to get a numerical vanishing for other type of classes. But then it goes down to the problem of essentially complex geometry. So this is a generalization of the JBT branch. So the question is, can you get other relations of this type? And in general, it would be nice to know for which range is I, G, RS, mu, lambda, for which range they value, or any linear combination of them value. Maybe another thing I can say for the one way to interpret this relation, that if you have indices here, which are too big, this relation is going to give you a way to express in terms of i's with lower insertions until you get to something which is bounded insertions, and then actually it's 0. Some integrals are unstable.
On the green part.
Questions?
Yeah. Can you say what like the bounding condition? Like why is it there?
So the boundedness condition in JPT, because when you do this localization, you don't want contribution from some boundary starter, from some boundary. And the boundedness condition allows you to do that. Otherwise, I guess you would have contribution from other boundary strata, which they have not analyzed. And I guess if you were analyzing them, then at least in the case I want to get to this type of integral evaluation. So that I'm pretty confident that can be done by efficiently able persons. But for argument from S or from the other ones, I would be very happy to hear of any ideas to try to get. Okay, so two other types, two other theorems like this. The two other vanishing conditions I get, in fact, this time depends on genus. They're only going to be true for genus small enough. So theorem 2 is the setting where R is the S again, but this time E bigger than 2 and X bigger than 1. And in that generality, there are some rather complicated vanishing involving 3 partitions. So here I'm only going to state for the patterns for S equal 1, where it's a bit simpler and on 2 partitions. So directly going to write what the vanishing is, not the corresponding everything it is. So you take tau, which is an particle with size more than r minus 1. Then this should be smaller than d at r minus 1. And if this is true, then you have the following relation. It's always a sum. Some alternating signs. And you have to decompose now your tau in k partitions by merging some rows. But now you have the condition that the size of each of these rows between 2 and r minus. Then you have some explicit combinatorial factor. Different than the other one. And I, V, so here I was doing S equal 1 in that example. And here you have mu, and the other twist is R plus 1 minus rho, 1 minus sine equal 1, and so on. So this is here. And if furthermore, tau has no line parts and is bounded in the sense that when you go to rows, you get something with size bigger than R. Then again, there's only one term here, and we use that y g bar s r plus 1 minus tau is 0.
Now, press the red button on the left.
Sorry.
You have to press the red button on the left so that the light is on. And right on. Like working.
Make all the light be yellow.
And then rotate the other way.
And then one. I don't yet choose which one.
Can I ask you another question? Do these satisfy some properties like a factorization for you, like
So the Chiodo classes for S between 0 and R, and for the A's in the fundamental range are coexistents.
and so then do they form homomorphic fields?
Yes, so the Chiodo classes in the good range are coexistents.
Okay,
In
and
the
so
range I
then
use them, they
is
are.
this vanishing coming from the fusion rule vanishing?
I don't have a geometric reason for what. Yeah, and you raise the one of them.
Line is red to the left, you still need to push the button.
What is that?
The issue is the direction, yeah.
Sorry, can I ask one more question?
Yes.
Are they globally generated, the push bar, the moduli space in terms? On like, for example, in GDC?
Can you speak louder?
Are those sheaves that you, when you push them forward to M0, and are they globally generated? Do you know that they're the image of the?
Well, you see the way these Chiodo classes are constructed, you take a dy, push forward.
Yeah.
You have some complexes of sheaves. In
So
general,
you-
it's not.
Wow.
In general, it's not just a sheaf. It's a virtual. I mean, it's a complex. It's not only. I mean, you have to do a dy push forward in general. You can construct some classes in certain cases, like the negative with an R spin class or number a theta class, where it indeed is just you just take a first dy push forward, and that's accurate.
And do you know anything about that?
So there are also vanishing of vacuum that you can sometimes express geometrically of this kind for these other classes, but it's not the same class that I work here.
So yeah, I don't think this question is really. Because the study of the
Sorry.
the direction of the study has been about I don't think anyone's considered this question about when, if you have vanishing, there's only one object, or whether there's no generation.
No, but what you can do, you can look at this theta class or this negative with an R spin class, for example, this evolution of Norbury and Kazarian. And that you could prove by actually similar techniques. That's what Gaëtan, Shidamara, and GAUS did. And you can do actually some techniques are a bit similar in spirit to the way I put that. So maybe it's going to be a bit more clear what kind of generality one can hope to get at the end. Here 3. So that's a case where it's not necessarily divisible. And now if you take some partition pi, which is smaller than r, which has part smaller than r minus s. So that's tau 1. And 2g minus 2 plus LU x plus mu plus tau is smaller than r plus s. Then tau minus r. Then you have that the sum and here there's no alternating signs. It's again a sum of decompositions of this tau. And the defining condition that okay, the size of each of the parts could be smaller than r plus s minus 1. And rho I has parts between s and r plus s minus 1. And then you have again some combinatorial factor I v r s mu r plus s minus 1, which is equal to 0. All these relations that you mentioned, these were proved in a joint one with Max Harrod and Daniel Levansky. And so I say there's no theoretical reason for that to be true, but also you don't guess some equation and then you say, okay, I guess them and then I prove that. We use topological recursion, and I'm just going to explain roughly what is the machinery. And then you just compute, and at the end you get relation. And if you have an extra argument to say that this thing should vanish, which is a polynomiality argument, then you get this value. So some of the complicated structure here is something which comes from the computation. There's nothing to guess. Okay.
We think that all these statements they build out like the degree of a certain polynomial is something so beyond.
That something is a polynomial, although it shouldn't be for just intersection theory reasons.
Yeah.
So this is a totally different story at first. You consider a Riemann surface equipped with two meromorphic functions. And you are meromorphic functions. You assume that Dx and finitely many duals and basically want to see this some optimal C about the grand cover and the zero that are ramification points by holding round. And this state one for O This has nothing to do with the Hurwitz term. We don't want to cancel it. This is an auxiliary object. We're going to care about its complex geometry. So omega 02, it is a bidirectional, which has a double cone on the diagonal, which is symmetric, and the coefficient of the double cone is 1. And this is an important object that's going to allow representing neural forms in terms of holomorphic curves. So we can consider a map which I call omega 02 hat, which goes from, let's say, meromorphic forms with all only identification points. What you do, you just take the holomorphic form, and then you're going to compute the sum of residues at the ramification points of this branch cover of the primitive of omega 02 with respect to one variable. So it's a function with respect to z, locally defined, and then you compute the residue times phi z, which is the one form. So I get the z disappear, and I get still a one form with respect to omega 02 because that with respect to 0 because that was a pi. The one form with respect to that order. This property implies that omega 02 is a projective. I'm going to denote the image in detail. We start from spec vector S. Quadruple. Technological function is going to produce for you omega Gn whenever 2d minus 2 plus n is positive, which is an element of d tilde tensor n. So it goes so in a very specific way, which I'm not going to write. But essentially, you look at a certain combination of the omega g prime n prime, or 2g prime minus 2 plus n prime, more than 2g minus 2 plus n. You get one form, you just look at the image, and that's how you get your negative. So it's a clear post. Let's read to that. I don't want to write the form, the non-forms. It's some expression.
Now, what's the tilde?
V tilde is the image of this projective. It's a subspace of the space of meromorphic form disposed at connectivity. So these are dependent n variables on the curve, and you suppose exactly when one of the variables goes to replication. And this construction has several properties which are relevant for us. The first property is that under some weak assumptions, there is the spectral curve you can attach omega s Dn, which is the topological class. Maybe depending on some indices. And here, I'm going to put myself in a setting where the X in the neuromorphic and sigma is compact. So that will take P1. And in that case, I also have an operator D, which takes one form divided by the X, and then different thing. I'll give you one form with higher order poles that computation force. And this B Chiodo is a finitely generated D module generated by some state B. It's 38 plus B. There's some primary differentials. You have double poles, and then you get all other differentials by acting with this differentiation. And that's what the operator plan depends on. Choice of primary differential for each residual. For each concern.
So this mean you choose or it's some.
No, this is part. So in this case, it's involved. The construction of. And this is done in such a way that only at the end, it is the integral over NBN of this class with I classes we explain that in geometric series, when you have psi I to the k come with a di to the k, we let this di act on the I copy of B, which is here. And that's what we get. So this is a linear combination of neuromorphic forms, which are in Chiodo, whose coefficients are intersecting. Example, I love the Chiodo class. You get it by taking actually sigma equal to 1. And I'm keeping it because X has a log that is dx neuromorphic. Okay. And if X log of sigma is equal to the R, Y is equal to the F. And as value factor, we don't have a choice on P1 is only 1. Z1 is 2 over Z1 minus Z2. So here, I also didn't write that into this construction, but it's explicit. And if you apply the construction to exactly that curve, you get a geometry. There's two more things that it needs. Property, but one side the differentials, what you want to do is in fact to expand them near some points. You get coefficients, and these are typically they count something inference. That here is odd. And solve interesting numerical problems. What I mean here, I'm going to be concerned with stage the point P, in the simple form of x, of dx. We can write this kind of coordinates side here centered at this point dx like this. Then you can look at the coefficients. So you can expand omega dn from all this I with G. And you're going to get some coefficients H, D, and mu, psi 1, mu 1, psi n, mu n over mu 1 to n. And these numbers are what you want to extract. You choose well your spectral curve, you can get weight service numbers here. That's the result which has been proved in various versions, more sophisticated, and now there's a more quite general statement involved. Not class of weight service. The last ingredient is that you want to vary the spectral. And by the various spectral curve, maybe if you take a family spectral curve, it is singular at some value of the parameter. And you want to analyze, okay, how singular can it be? What happens here? Three. Yeah, person, and I didn't family. So you can look at the relative sheaf of differentials. So you have the space of neuromorphic differential varying with the moduli of the family, and on that you can define a connection by working at projection of the points x projection. Oh, neuromorphic. And constructed as the following nice property is that if I do dt of y dx, and if you can represent this by a holomorphic current, here's the 2. That's a holomorphic form equally. If you can represent by a certain holomorphic currents, it is the term of holomorphic form on the cycle gamma t, then under some assumptions, you know that dt omega dn is going to be expressed by the same holomorphic currents there. With omega dn equals 1. This allows you to write omega dn t as a Taylor series. You can write a bar and the omega gn for the T deformed spectral curve in terms of essentially the omega, all the collection of omega gns on the T equals 0, the central fiber. Okay, so with this, here is how we get the spectral curve that we consider. So remember, I have my Chiodo class like this. And the idea is to try to deform these curves to get to a curve that counts whose omega gen are counting parameters. So the definition that we want here, we have R equals S. This is some of Q when with A plus Q S S with S over D. And this is some plus S D to the S. And I got a T here. T equals 0 up to this again. This totally for class is the Chiodo class. At T between 0, the numbers which I get are weight Paris numbers. So you can express weight Paris numbers in terms only on the Chiodo class by using this data set. However, so you get something polynomial in the Q, but here, if you set QS equals 0, the degree jump. You have less ramification points. So how to go in? Because you're really using, when you construct with operator reference, you reduce the ramification points. If your number of ramification points change, then your construction can be very close. So a priori is going to be singular than QS equals 0. But the combinatorial interpretation tells you that actually, yes, the term is singular, the omega gn may be go up, but the numbers you extract from these flat periods at z equals actually z equals 0, they are regular. These numbers, H, D, and E, are actually polynomial. Also in QS. By combining these two facts, the Taylor series, that's what I can tell you, gets an expression of the intersection numbers, including negative powers of QS. With the polynomiality here, you get this actually negative power should have 0. We just have we found two other families, but we have an argument either from Paris theory or some other technical aspect. But we know this polynomiality, so we can conclude, and that's how we found these formulas. Everything comes from the combinatorics of these polymorphic parallels describing those definitions. Sorry for the